The objective of this lecture is to provide an introduction to kinematics and the Transport Theorem. This lecture will be divided into the following parts. First, we will describe the objectives of kinematics. Next, we will describe the key concepts of reference frames and coordinate systems. And using the concepts of reference frames and coordinate systems, we will discuss rates of change of scalar and vector functions, and then, using the basic constructs of rates of change of scalar and vector functions, we will derive the rate of change of a vector in a rotating frame Next, we will describe some additional key properties of the Transport Theorem. And then finally, a simple example will be studied. That highlights the structure of the Transport Theorem. So let's start this lecture with the objectives of kinematics. So kinematics is the study of the geometry of motion without regard to the cause of the motion. Now, what the statement means is that in kinematics, we're not interested in why the motion is occurring. We're just trying to characterize what is actually happening or what the motion is. So as a result, kinematics is concerned or focuses on the position, velocity, and acceleration of a point, and also focuses on the rotational motion of what is called a reference frame equivalently a rigid body. And we're going to go into details on all of this stuff. But what's important is that these are the key aspects of kinematics that this study will focus on. Now, in order to get started, we need to define several things. So the first thing we need to define is we need to define a concept of a reference frame. So recall that motion takes place, or motion occurs, in three-dimensional Euclidean space. Which is denoted E3. Now, in three-dimensional Euclidean space, we have several objects that we need to be concerned with. These objects of interest are points, vectors, and reference frames. We will describe each of these in turn. So the first thing we're going to do is describe a point, then we're going to describe vectors, and then we'll describe reference frames. So let's start with the concept of a point. So what is a point? A point is a zero-dimensional object in E3. So when you think of a point, you can think of a point the same way you would always think of a point. It's like a dot. So if I have a point O, then that takes up no physical space. Similarly, if I have another point P, that takes up no physical space. These are examples of points. Now, points can actually be used to generate what are called vectors. So a vector is any quantity with magnitude and direction. Now what's important about vectors is that vectors are created from points. So again, if I have a point O, suppose I have a point O, and I have another point P. If I take the directed line from O to P, so if I go from O to P, that creates a vector. The vector has a length, which is the distance between the points O and P, and it has, which is its magnitude, and then it has a direction, which is the unit vector in the direction from O to P. So if I call the vector from O to P, let's just arbitrarily we call this thing RP relative to O. That's the vector from O to P. Then the magnitude of that vector, which, as we learned in the vector algebra discussion, is equal to the square root of RP slash O dotted with RP slash O. That's equal to the magnitude of RP slash O. And finally, I'm just going to call this thing U. U is equal to RP slash O divided by the magnitude of RP slash O. And that's the direction of RP slash O. So you can see now that given this whole construct, the vector RP slash O can be written as its magnitude times its direction. And that's how any vector can be written. It's magnitude times its direction. Now, the next thing we have to describe is we have to describe this very specific construct of what's called a reference frame. Now, this is important because when we observe motion, we are ultimately going to be observing motion in what's called reference frames. So what I'm going to do now is I'm going to define a reference frame. So a reference frame is defined as follows. It's a collection of points and it's a collection of at least, this is important, at least 3 non-collinear points whose distance from one another is constant. Now, this can be depicted, this concept of reference frame can be depicted as follows. Suppose I take this collection of points, and suppose I pick 3 points. I'm just going to arbitrarily pick 3 because I need at least 3. And I'm going to say that these 3 points never change their distance from one another. And I'm going to label these points O, Q, and P. So if I connect these points to one another, these points never change distance from one another. So if I take the distance between any 2 of these points, suppose I take the distance from between Q and P, I can call that dQP. Now, that distance, which I've defined, is constant. So dQP is constant. I'm going to write that down in just a minute. But this collection can move. And the collection can move so that at some later point in time, this collection qualitatively is in a different orientation from where it started. But I still have these 3 points, which are part of this collection. And the distance between these 3 points is the same as what it was in the first orientation. So no matter how I move these points, these distances never change. So suppose this consists of, or this corresponds to t equals t1, sometime t1, and this corresponds to t equals t2. And this entire collection has moved in going from t1 to t2. This distance, dpq, or dqp, is constant. And this is true. This distance being constant is true for all points in this collection. So we schematically denote this reference frame as A. So we say A is a reference frame. In this case, it's just an arbitrary reference frame. I haven't explained what to do with it. Now, once we have a reference frame, we can actually describe quantitatively information in that reference frame using what's called a coordinate system. And the way we describe a coordinate system is as follows, is that we pick a point that's fixed in the frame, and we call that an origin, and that's the point from which all distances are going to be measured in that frame. And then we have to pick 3 vectors that are fixed in the frame, and those vectors form a basis, and that basis becomes a basis that's now fixed in the frame that we're dealing with, whatever this frame happens to be. So we'll do that next. So let's talk about coordinate systems. So within any given reference frame, and we'll just call this reference frame A coordinate system that is fixed in the reference frame is defined as follows. So first, we need an origin, which is a point from which all distances are measured. Now this point is called an origin, and this point has to be fixed, must be fixed in the reference frame. When I say the reference frame, I mean the reference frame of interest, whatever reference frame we're dealing with. The second thing is we need 3 mutually orthogonal vectors, which forms a basis, or a right-handed orthonormal basis. Now we can put these two things together if we have a frame and then 1 and 2. So frame together with 1 and 2 provides both qualitative and quantitative information about motion relative to the reference frame of interest. Now, we can put this together in a picture, as we'll do in just a moment. So here's a schematic that describes what I just wrote down in words, which is, here's a frame, and I'm arbitrarily going to call this frame A. I have a point, O, which is an origin. Now this point, it's very important that this point be fixed in the frame. So O is fixed in the frame, which in this case is A. So it's fixed in A. And then I have 3 vectors which form a right-handed orthonormal basis, and I'll just qualitatively draw these vectors. And I'm going to call these vectors E1, E2, E3, and this basis E1, E2, E3 is fixed in A. Now once we have that information, we can describe any point measured relative to O, because O is the point from which we're measuring distances. And we can describe it in the basis that I've provided. Now, it's really important to understand that O, together with this basis E1, E2, E3, that's the coordinate system. And it's a coordinate system fixed in A. Now, we're going to abbreviate bases in the following manner, is that we're going to say let E equal E1, E2, E3. So therefore, the coordinate system becomes O together with E. Now once we have this construct, suppose that we have an arbitrary vector. Doesn't make a difference what this vector is. So we say let B be a vector. Then B can be expressed in the basis E as, and we write down B is equal to B1 E1 plus B2 E2 plus B3 E3. Now, once we have that description of B, or the expression of B, we now know that we have a way of being able to describe this vector B in a basis that's fixed in reference frame A. Now, what we need to do in kinematics is we need to describe how vectors change with time. And this is a very important construct. So the first thing we need to do is we need to have a few properties of vectors, which is that vectors are quantities with magnitude and direction. And vectors do not depend on coordinate systems, and they do not depend on reference frames. So that's the next thing we're going to discuss. So these are key properties of vectors. The first key property is that vectors do not depend upon reference frame. What do I mean by that? What I mean is that if I say B in reference frame A, that's equal to B in reference frame B for all reference frames. A and B. So that just means that we can just drop the reference frame and we can just say B is equal to BA is equal to B, and so we don't have to have a reference frame at all. So we just use B. So simply B is enough. The second thing is that vectors do not depend upon the choice of coordinate system. What does that mean? Well, what that means is this. It means that, suppose that we have two bases. We've got E, which is E1, E2, E3, and it's fixed in A. But we also have another basis. I'm going to call it U, which is U1, U2, U3. And it's also fixed in A. Then B is equal to B1E E1 plus B2E E2 plus B3E E3 is equal to B1U U1 plus B2U U2 plus B3U U3. It doesn't matter which coordinate system I use or which basis I use to express the vector. It's the same, which means vectors are coordinate free. coordinate-free quantities. And up here, this means that vectors are reference frame free quantities. Now, once we have all this, now we need to describe how vectors change with time. And this is the next important concept. So we need to deal now with rates of change. So rates of change fall into two categories. We have scalars and vectors. So the first thing here is we need to deal with rates of change of a scalar. So rate of change of a scalar function of time. That's the first key concept. So suppose when we say let x of t be a scalar function of time. So what that means is x of t is an element of the real numbers, because remember, a scalar is an element of the real numbers. So then the rate of change of x of t follows the usual calculus definition, is that dx dt is equal to the limit as delta t approaches 0 of x of t plus delta t minus x of t divided by delta t. And this is abbreviated x dot of t. That's how we abbreviate it. Put a dot over the x. That means dx dt. Now that's okay for scalars, but for vectors, it doesn't work quite so simply. So now we have to deal with rate of change of a vector function of time. Now, in this particular case, the rate of change depends upon the reference frame. And we can see that as follows, is that suppose b is a vector function of time. So we're going to say let b of t be a vector function of time. Now, if I'm standing in one frame and I'm watching this vector b, it's going to look as if it's doing something different from if I were standing in another frame. And the reason is because the vector, while its magnitude and direction is the same in all frames, how an observer in that frame actually views the vector changes depending upon the perspective that the observer has. So the rate of change of the vector depends upon the reference frame used to observe the vector. So what that means is as follows. So suppose A and B are distinct reference frames. Then the rate of change of the vector B in frame A in general is not going to equal the rate of change of the vector B in frame B. So if I'm standing in two frames, so I suppose I have two frames here, I'll put down one frame, and I'm just, for simplicity, I'm just going to assume that there's a point from which distances are measured, and that point is fixed in both frames. So I'll just say here that O is fixed in A and B. And here's A, and here's B. Now, if I have a vector, if these two frames are moving different from one another, I'm going to see that vector changing differently. If I'm standing in frame A, it's going to look like the rate of change of that vector is different from what its rate of change of would be in frame B. So as a result, I have to figure out now, if I'm going to be observing motion in one frame or observing motion in another frame, how does one relate the rate of change of a vector in one frame to the rate of change of a vector in another frame? So this becomes a key question, was how is the rate of change of a vector relative to one reference frame related to the rate of change of that same vector in another reference frame. That's a key question. So in order to be able to answer this question, we have to do the following. This is the way in which this question gets answered. Is the first thing we need to do is we need to find a way to quantitatively describe this vector in one of these two frames. So in order to be able to start this process, I'm going to categorize each one of these two frames. So going back to the diagram, I have a frame. I'll call this frame A. And there's a point here that's fixed in this frame, and there's another frame here, which I'm going to call frame B. So here's frame A, here's frame B, and once again, this point, O, is fixed in A and B. Now, I'm going to define these two frames as follows. I'm going to say that B is what's called the observation frame. And I'm going to call A the target frame. What I mean by that is that the observation frame is the frame in which I'm standing and I can see what this vector B is doing. There's my vector B. And I can see what the vector B is doing. So given that B is my observation frame, I'm going to attach a basis to frame B. Now this is important. This basis is fixed in frame B. It's not fixed in frame A. I'm going to call this basis E1, E2, and E3. So E is equal to E1, E2, E3. And it's fixed in B. It's not fixed in A. Now given that I'm able to fix a basis to frame B and I'm making all my observations in frame B, I can now describe quantitatively this vector B in that basis E1, E2, E3. in order to be able to sort of emphasize the concept of an observation frame, imagine that you had a camera. So here's my camera. And this camera is fixed in frame B, and it's watching everything from the perspective of an observer fixed in frame B. So now B, which is my vector, can be written as B1 E1 plus B2 E2 plus B3 E3. Now, if I take the rate of change of this vector in frame B, what do I get? I get, well, now I'm taking the rate of change. So since scalars, their rates of change don't depend on reference frames, they're just scalar functions. I can write this as B1 dot E1 plus B2 dot E2 plus B3 dot E3. But then I have three other terms, which are B1 dE1 dt in B plus B2 dE2 dt in B plus B3 dE3 dt in B. But recall that this basis is fixed in B. So because this basis is fixed in B, it means that these vectors are all fixed in B, which means that their rates of change in B have to be 0. Because if they weren't 0, they wouldn't be, those rates of change weren't 0, they wouldn't be fixed in that frame. So that means that these last three terms here, this whole thing goes to 0 because all three of these rates of change are 0. So what that means is that the rate of change of the vector B as viewed by an observer in frame B, which is what this notation means, is just the first three terms. So now we'll go into what this terminology means and how we're going to use it as the starting point for the next step in the process. So, using the description from the previous page, we have that dEI dt in B is 0, and that's because E is fixed in frame B, which leads to the following result. So we then have that dB dt in B is equal to B1 dot E1 plus B2 dot E2 plus B3 dot E3. So now, ultimately, what we want is we want the rate of change of the vector B in frame A. And in order to be able to obtain that rate of change, we have to work with these basis vectors E1, E2, and E3. So the key properties that we need to start with these basis vectors is, the key property is that we know that EI dotted with EJ equals, well, it equals one of two things. It equals 1 if I is equal to J, and it's equal to 0 if I is not equal to J. And that's just because these are basis vectors, so they all have unit length. They're all unit vectors. So if I take the dot product of any one of them with themselves, I get 1. If I take the dot product of any one of them with any one of the others, I get 0 because they're all orthogonal, because E is a right-handed orthonormal basis. So then the next step in this process is that we want to obtain expressions for the rates of change of these basis vectors in frame A. So recall that the rates of change of these three basis vectors in frame B are 0 because these vectors E1, E2, and E3 are fixed in frame B, but they're not fixed in frame A. So the way we're going to go about doing this is we're going to work with the rate of change of EI dotted with EJ. Now, that is a starting point, will get us expressions for these rates of change of these three basis vectors, DEI, DT, and A, as we'll see in the next step. So now let's look at this rate of change of EI dotted with EJ. So note that EI dotted with EJ is a scalar. So that means that I can take the rate of change of this scalar in any frame, and it doesn't make a difference because the rate of change of a scalar doesn't depend on the frame. Because remember that when we define the rate of change of a scalar, we just said dx dt if x is a scalar function of t. So d dt of EI dotted with EJ is equal to 0, and this is independent of reference frame. So that means that we can arbitrarily take this rate of change in any frame that we feel like taking it in. So arbitrarily, take the rate of change in frame A. So what do we get when we do that? So that means d dt of EI dotted with EJ is equal to d dt in A of EI dotted with EJ, which is 0. So if I expand this out using the product rule for differentiation, that gives me dEI dt in A dotted with EJ plus EI dotted with dEJ dt in A has to equal 0. Now this tells me that dEI dt in A dotted with EJ is equal to minus EI dotted with dEJ dt in A, which for completeness, because the dot product is commutative, is equal to dEJ minus dEJ dt in A dotted with EI. So in order to make this notation a little bit more tractable, let's say let omega ij equal dEI dt in A dotted with EJ. So what we get when we do that is we get omega ij is equal to minus omega ji. Now, using this construct, we can actually figure out how to expand or express, I should say, these rates of change of these vectors dEI dt in A. So now, let's look at this. So we have omega ij equals minus omega ji. Now first, if I is equal to j, then that implies omega ii equals minus omega ii. But the only way that can happen is if omega ii is 0. So the only number that's equal to its negative is 0. So omega ii has to equal 0. So that special case actually allows us to now to be able to write these, use these omegas to actually expand out these vectors, which is, we know that dEI dt in A dotted with EJ is the component of dEI dt in A along EJ. That's the definition of a component, right? If I take the dot product of a vector along a particular direction, then the dot product in that direction is the component of that vector in that direction. In this case, I'm taking the dot product of dEI dt in A along the direction EJ, so dEI dt in A dotted with EJ is the component of dEI dt along EJ. So if I use that construct, I can now write each one of these rates of change in the following way. Well, this is equal to omega 1 times E1, but there is no omega 1 because omega 1 is 0 because all of the omega ii's are 0. So this gives me omega 12 E2 plus omega 13 E3. Similarly, dE2 dt in A is equal to, well, because these components omega ij are equal to negative omega ji, I get minus omega 12 E1, and then I get plus omega 23 E3. And then the last rate of change, which is dE3 dt in A, is equal to minus omega 13 E1 minus omega 23 E2, where the terms along the diagonal are all 0 because omega ii is 0. Now what I'm going to do is I'm going to make the following substitutions. So here are the substitutions, which is I'm going to say let omega 12 equal omega 3, omega 13 equal minus omega 2, and omega 23 equal omega 1. And we'll do that on the next page. So let omega 12 equal omega 3, omega 13 equal minus omega 2, and omega 23 equal omega 1. Now, if I do that, what I wind up getting is I wind up getting dE1 dt in A, which is equal to omega 12 E2 plus omega 13 E3 is equal to omega 3 E2 minus omega 2 E3. The next one is dE2 dt in A, and that's equal to minus omega 12 E1 plus omega 23 E3, which is equal to, well, omega 12 is omega 3, so this is minus omega 3 E1, and then omega 23 is equal to omega 1 plus omega 1 E3. And then this third rate of change is equal to, I've got minus omega 13 E1 minus omega 23 E2, which is equal to, well, omega 13 is equal to minus omega 2, so this is omega 2 E1, and omega 23 is omega 1, so I get minus omega 1 E2. Now this becomes a really useful way to be able to write things. All I really did here was just a substitution. Instead, I only have 3 coefficients left, so I just replaced them with 3 single index coefficients instead of having 3 double index coefficients. So it's simply just a replacement of symbols. That's all it is. But suppose now that I say let omega BA equal omega 1 E1 plus omega 2 E2 plus omega 3 E3. Then I can use this vector to replace what I have up above, which is that, look what winds up happening when I take this vector and I take its cross product with all 3 of these vectors, E1, E2, and E3. So omega BA crossed with E1 is equal to, well, what do I get? Well, I've got omega 1 E1 plus omega 2 E2 plus omega 3 E3 crossed with E1. E1 crossed with E1 is 0. E2 crossed with E1 is minus E3. And E3 crossed with E1 is E2. So I get omega 3 E2 minus omega 2 E3. If I take omega BA and I take its cross product with E2, I get a similar thing. I take the whole thing and I take its cross product with E2. E1 crossed with E2 is E3. So I get omega 1 E3. And E3 crossed with E2 is minus omega 1. So I get minus omega 3 E1. And then the last one, which I'll put over here, is I get omega BA crossed with E3 by the same logic. I've got E1 crossed with E3 and E2 crossed with E3. E1 crossed with E3 is minus E2, and E2 crossed with E3 is E1. So I get omega 1 E2 minus, I get omega 2 E1 minus omega 1 E2. So that gives me all of the information that I need to be able to be able to substitute now these expressions up above. So now if we do these substitutions, what we actually find is the following. So we then have dE1 dt in A is equal to omega BA crossed with E1. dE2 dt in A is equal to omega BA crossed with E2, and dE3 dt in A is equal to omega BA crossed with E3. And using these three relationships now, we now have the following, which is that suppose we compute dB dt in A. So what do we get? So dB dt in A is going to equal, well, remember that B was equal to B1 E1 plus B2 E2 plus B3 E3. So this is going to give me B1 dot E1 plus B2 dot E2 plus B3 dot E3. Now remember that E is fixed in B. It's not fixed in A. So there are going to be three other terms that are going to come out of this. They're going to be dE1 dt in A, because these basis vectors are not fixed in frame A. They're fixed in frame B. And so from the product rule for differentiation, I wind up with these three additional terms. But notice that the first three terms here are just the rate of change of this vector in frame B. So now what I get is I get the rate of change of the vector in frame B plus these three additional terms. So now I can write this as follows. So we end up with dB dt in A is equal to dB dt in B plus these additional three terms, which are B1 times dE1 dt in A plus B2 dE2 dt in A plus B3 dE3 dt in A. But if I substitute in now, I get the following results. I get dB dt in B plus I've got B1. Well, what is dE1 dt in A? It's omega BA crossed with E1. And what's dE2 dt in A? Well, that's omega BA crossed with E2. And then the last term is plus B3 omega BA crossed with E3. And so now this can be simplified further to give me dB dt in B. And because the cross product can be factored out of all three of these expressions, I wind up with omega BA crossed with B1 E1 plus B2 E2 plus B3 E3. And that expression in parentheses is simply the vector B. So this gives me dB dt in B plus omega BA crossed with B. Now this last result is what's known as the transport theorem. This is what's called the transport theorem. And what it does is it allows me to be able to compute the rate of change of a vector in one frame, given that I know its rate of change in another frame. But in order to be able to do that, there's a vector that's intermediary that is part of this transport theorem, which is this omega BA. Omega BA is what's called the angular velocity of reference frame B as viewed by an observer in reference frame A. And it's what connects the two frames. In other words, if I know how reference frame B rotates relative to reference frame A, and I know how the vector B is changing in reference frame B, then I can determine how the vector changes in reference frame A. And that is the starting point for being able to do kinematics between reference frames, because in general, you won't have just one reference frame in order to make your calculations convenient. You're going to have multiple frames, and they're going to be rotating relative to one another. Now, there are a few key properties of reference frames that are useful to derive. The first one is if you have more than two frames. So if you have more than two frames, then you want to be able to add the rotations or add the angular velocities in the proper way. So the way we're going to do this is as follows. We say let A, B, and C be reference frames. So then we have the following. We know that from the result that we just derived, the transport theorem, that dB dt in A is equal to dB dt in B plus omega BA crossed with B. But we also know that dB dt in B is equal to dB dt in C plus omega CB crossed with B. That's just simply another application of the transport theorem between frames C and B. So if we substitute the second result into the first result, we get dB dt in A is equal to dB dt in C plus omega CB crossed with B plus omega BA crossed with B. And again, I can take the cross product out on the right this time with B, and that gives me dB, dt in C plus I get omega CB plus omega BA crossed with B, which can be rewritten as dB dt in C plus omega BA plus omega CB crossed with B. So that gives me a way to be able to relate the rate of change of this vector A, of this vector B in frame A, relative to its rate of change in frame C. But you'll also notice the following result. And that result is that dB dt in A, if I go directly between frames A and C, that's equal to dB dt in C plus omega CA crossed with B. So if I equate this result with the previous result, I wind up with omega CA is equal to omega BA plus omega CB. This is what's called addition of angular velocities. And it's a convenient way to be able to write it. You can see that you go from C to B and you go from B to A if you read this equation from right to left. So that's a nice thing about this. The next thing is, which is we need to deal with one more derivative often in angular velocity, which is what's called the angular acceleration. So suppose we take the rate of change in frame A of omega BA. Well, from the transport theorem, that's equal to the rate of change in frame B of omega BA plus omega BA crossed with omega BA. But any vector crossed with itself is 0, so this just tells me that d dt in A of omega BA is equal to d dt in B of omega BA. And this quantity is defined as alpha BA, where alpha BA is what's known as the angular acceleration of reference frame B as viewed by an observer in reference frame A. So first, let's review the transport theorem. So recall from earlier that the transport theorem is written as follows. Given a vector B, the rate of change of B in reference frame A is related to the rate of change of B in reference frame B as dB dt in A is equal to dB dt in B plus omega BA crossed with B, where omega BA is the angular velocity of reference frame B as viewed by an observer in reference frame A. So now let's look at the transport theorem visually through a picture to provide an understanding as to what is going on with the different terms in this theorem. So recall that it is assumed that frames A and B share a point. Let this point be O. So here's frame A, and here's frame B. And there's a point O, which is common to both frame A and B. So what I mean by that is that O is fixed in A and B. O is fixed in A and B. Now I have a vector. This vector is just an arbitrary vector, B. And what's happening in the transport theorem is as follows, is that suppose we have an observer that's fixed in frame B. And I'm going to denote this observer visually as a camera. So there's a camera that's fixed to frame B. And this camera is watching this vector. And what the camera sees as the frame moves and as the vector changes is the camera sees how vector B is changing in reference to reference frame B. Here's reference frame B and here's reference frame A. So there's a camera. I'm going to call it an observer. So an observer fixed to frame B sees the vector B changing in a particular way. And this rate of change is the rate of change of B as viewed by an observer in reference frame B. But what an observer in reference frame A sees, if I fix a camera to reference frame A, now this observer is fixed in reference frame A. And the observer in reference frame A doesn't see the same thing that the observer in reference frame B sees because frame B is moving relative to frame A. So whatever this vector B is doing, it appears to be doing something different in reference frame A from what it's doing in reference frame B. So because reference frame B moves relative to reference frame A, an observer in reference frame A sees B changing different from the change in B seen by an observer in reference frame B. So what does that mean? So that implies that the rate of change of B in reference frame A is not equal to the rate of change of B in reference frame B. And of course, I'm assuming here that the frames A and B are not the same frame. So assuming that they're not the same frame. But what is it that relates these two rates of change? So that, of course, calls into question, how do you relate these two rates of change? So the question then becomes, how is it possible to relate dB dt in B and dB dt in A? And that connection is obtained through this quantity called the angular velocity. So the answer to this is these two rates of change are connected via the angular velocity of B relative to A. Now, this is still somewhat abstract, so it is a little bit easier to be able to see this through example, and then we have to get into quantification of these rates of change using particular coordinate systems, which is what we're going to do now. So rather than continuing with the abstractness of two frames and a vector, we're actually going to use an example now to show how all of this plays out. And this example is also going to demonstrate how coordinate systems should be used when solving problems of this kind. So this example is a fairly simple problem, but it's designed to be simple because by it being simple, it makes it possible to be able to see exactly what's going on without introducing unnecessary complexity. So what we have here is we have a disk of radius r rotating on a surface. Now, I'm going to call the disk, this is my terminology, I'm going to call the disk it's going to be denoted by D, and the surface, which I'm going to call the ground, is going to be denoted by G. And this is what I'm calling the surface. This is the surface on which the disk rotates. Now I'm going to draw the picture that corresponds to this. So here is the disk. So the ground is here. And here is the disk. And I'm going to call the center of the disk O. All right. Now, in order to make this a little bit easier, O is going to be fixed in D and G. Now, that's the same picture that I had earlier when I said that there's a point common to both frames. I called that point O in the abstract notion, and I had frames B and A. I'm calling it O in this example, and the two frames are now D and G. Now, I'm going to put a point Q on the end of the disk. And the distance from O to Q is R because the disk has a radius R. So next, I'm going to introduce an angle theta, and I'll explain what this angle means in just a minute. Which is the angle theta is the angle formed between the direction OQ and a direction that's fixed to the ground. So this direction right here, this direction is fixed in G. So in other words, the disk is rotating relative to the ground, and the angle theta is measuring the angle formed by a direction that's fixed in the ground and the direction OQ. Now you can see that because O and Q are both fixed to the disk, so Q is fixed to the disk, and O is also fixed to the disk. That means that as a result of that the direction along OQ is also fixed to the disk. So that means OQ itself is fixed in D. And that implies the direction from O to Q is fixed in D. And that's the starting point for this problem. So the first thing that we're going to do is we're going to set up two coordinate systems. So I'm going to draw this picture again with a little bit less obstruction, and we're going to set up two coordinate systems. So I'm going to add to this picture the following. I'm going to add two coordinate systems, or two bases. The first basis I'm going to put on this diagram is going to be the basis EX, EY, and then EZ. And I'll define what all these directions are. Now we said that the angle theta is measured from a direction fixed to the ground to the direction OQ, where Q is fixed to the disk. So EX, so EX is the EX, EY, EZ is this basis that I've just defined. The coordinate system has its origin at point O. So this is going to be a ground fixed coordinate system. So this has its origin at O. And then EX is going to be equal to along, now I have to be careful, it's along OQ when theta equals 0. So of course theta changes with time because the disk is rotating relative to the ground. So theta is a function of t. I didn't actually say theta is a function of t, but it's not constant, so it's changing with time. And then EZ is the direction out of the page. And then EY is equal to EZ crossed with EX. Now this coordinate system is fixed in G. Now what I'm going to do with this is as follows, is before I introduce my second coordinate system, because I am going to introduce a second coordinate system, let's express the position of Q relative to O. So here's what we're after in this problem. So the objective is determine the rate of change of the position of Q relative to O as viewed by an observer fixed in D and G. Now, the first thing that we can see here is because O and Q are fixed in D, we know that the position of Q relative to O is also fixed in D. So what that means is the position of Q relative to O is fixed in D, which implies that the rate of change as viewed by an observer fixed to the disk of the position of Q relative to O has to be 0, because, as noted from the earlier material, that any vector that's fixed in a frame, its rate of change in that frame has to be 0. And so this last result is because the rate of change of a vector relative to a frame A is 0 if that vector is fixed in frame A. So we know now that the rate of change of this vector as viewed by an observer fixed to the disk is 0. Note, however, that the rate of change in G of the position of Q relative to O is not equal to 0 because Q is not fixed in G. Now, one way to do this, which is not the correct way or not a good way to do this, is to just naively work with this basis, EX, EY, EZ. So we can do that. So first, start by solving for the rate of change in G of the position of Q relative to O using the basis EX, EY, EZ. If we do that, we wind up with the following. So first, we know that the picture would look as follows. We have EX, EY, and we have this position of Q relative to O. And then we have this angle theta, and this distance here is R. So from this information, we know that the position of Q relative to O, it has two components. It has a component of R cosine theta in the EX direction plus R times the sine of theta in the EY direction. Now remember that this basis, EX, EY, EZ, is fixed in G. So as a result, we can take the rate of change of this vector that we have here, the position of Q relative to O, as follows. So then, because R is constant, and it's the radius of a circular disk, and EX and EY are fixed in G, we have that the rate of change in G of the position of Q relative to O is just going to equal d dt of R cosine theta times EX plus d dt of R sine theta EY. I haven't factored out the R yet, but R is constant. And the reason that it's simply equal to what I have here in the last expression is because these two vectors, EX and EY, are fixed in G. And as a result, that means that dEx dt in G is equal to dEy dt in G, which is equal to 0. So I would have a product rule. I'd have the derivative of the first times the second plus the first times the derivative of the second, but there is no product rule in this case because these basis vectors, EX and EY, are fixed in G. So as a result, I can now write that the rate of change in G of the position of Q relative to O is equal to, well, as I said, R is constant. So I just get R times d dt of cosine of theta times EX plus R times d dt of sine of theta times EY, which is equal to R. Now I have to be careful because I'm taking the derivative with respect to time. So the derivative of cosine theta with respect to theta is minus the sine of theta. So I get a minus sine of theta, but then it's times d theta dt. So I get minus R theta dot times the sine of theta times EX. Similarly, the derivative with respect to time of sine theta is cosine theta times theta dot. So I get plus R theta dot times the cosine of theta times EY. Now this quantity I'm going to call the velocity of point Q in G. This is the velocity of Q as viewed by an observer fixed in G. Now you can see that when I did that, I used purely the basis EX, EY, EZ, which is fixed in the ground. But that's not the best way to do this problem. It is a way to do this problem, but it's not the best way to do this problem. There's a much better way which takes advantage of the geometry. So now we're going to actually go back and we're going to take advantage of the geometry. So now let's add to the picture. So we're going to add to the picture a second basis. Now this basis is actually going to be fixed in the disk. I'm going to put a direction, I'm going to call that direction UR. And UR is going to be along OQ. I'll define all these below. UR is along OQ, and I'm going to define a direction UZ, which is actually out of the page, which is in the same direction as EZ. And then I'm going to define the cross product, which is going to be U theta, which is going to equal UZ crossed with UR. It completes the right-handed system. So now let's define this coordinate system. So I have the origin of this coordinate system at O. I have UR, which is along OQ. I have UZ, which is equal to EZ, and I already defined EZ. And I have U theta, which is equal to UZ crossed with UR. This coordinate system is fixed in D. Remember that OQ is fixed in D, so the direction along OQ is also fixed in D. Now, UZ is also fixed in D because its direction doesn't change relative to the disk, and it's equal to EZ in this particular case. Those two things happen to equal each other. And then U theta is UZ crossed with UR, and because UR is fixed in D, U theta also has to be fixed in D. So now you can see that when I do it this way, I can actually express the position of Q relative to O much more easily than I could have when I used the basis that was fixed in the ground. So let's do that now. So then, in terms of the basis, UR, U theta, UZ, the position of Q relative to O can be written as, or can be expressed as, the position of Q relative to O is equal to R times UR. Now you see that that's a much simpler expression from what we had before. It is equal to the expression we had before. What we had before was R cosine theta EX plus R sine theta EY. They are indeed equal to each other. But this expression, you can see, is much easier to write than the other expression. Now, not only is it easier to write, but now we can actually figure out the rate of change of the position of Q relative to O as viewed by an observer fixed to the ground. But now we have to use the transport theorem. Why do we have to use the transport theorem? Because we want the rate of change of the position of Q relative to O as viewed by an observer fixed to the ground, but we are expressing this position in terms of a basis that's fixed to the disk. So let's write that out in words. It says we want the rate of change as viewed by an observer fixed to the ground of the position of Q relative to O. Now, in this case, RQ relative to O is expressed in coordinates fixed in D, but it is desired to obtain the rate of change of the position of Q relative to O as viewed by an observer fixed in G. So as a result of the fact that we have expressed the vector in terms of coordinates fixed in D, and we want the rate of change as viewed by an observer fixed in G, we need to apply the transport theorem. So that implies that the rate of change in G of the position of Q relative to O has to equal the rate of change in D of the position of Q relative to O plus the angular velocity of D in G crossed with the position of Q relative to O. That's the transport theorem. Now you notice that in all three slots, the same vector appears. It's the position of Q relative to O because that's the vector whose rate of change we're trying to compute. Now we already know that the rate of change in D of the position of Q relative to O is 0. So we're going to start there. So we already know that the rate of change in D of the position of Q relative to O is 0 because the position of Q relative to O is fixed in D. So that first term in the transport theorem in this particular case is 0. So the next thing we need to compute the angular velocity of D in G. Now, let's go back to the diagram. So the diagram, now we can add to this diagram that basis UR, U theta, UZ. So there's UR, there's U theta, and then here's UZ. This angle is theta. Now, let's be really clear about this. We know that EX, EY, EZ is fixed in G. We know that UR, U theta, UZ is fixed in D. And this angle represents the angle between that direction EX, which is fixed in G, and the direction UR, which is fixed in D. So as a result, this angle leads to the angular velocity of D in G equaling theta dot times UZ. So what are these things? So let's go into even a little bit more detail so we can understand what all these things mean. So we have omega dg is equal to theta dot times uz. Now this quantity right here This is the rate of rotation of D relative to G. This quantity right here is the direction of rotation. Now, the direction of the rotation of D relative to G. Now, that direction of rotation, it's really important that it's understood that the plane of rotation is the EX, EY, or UR, U theta plane. But the axis of rotation is orthogonal to that plane. So if you curl your fingers in the direction of the rotation, your thumb will point in the direction of the axis of rotation, and that axis of rotation is UZ. So now we have everything we need to apply the transport theorem. So we recall that the rate of change in G of the position of Q relative to O is equal to the rate of change in D of the position of Q relative to O plus the angular velocity of D in G crossed with the position of Q relative to O. And this quantity right here we already know is equal to 0. So that only leaves these two quantities. So that means that we have 0 plus theta dot UZ crossed with RUR, which is equal to R theta dot U theta, which implies that the velocity of point Q as viewed by an observer fixed in G is equal to R theta dot U theta, because this velocity is equal to that rate of change. Now, let's look at the two expressions that we have. So we have that the velocity of point Q as viewed by an observer fixed to the ground is equal to minus R theta dot sine theta EX plus R theta dot cosine theta EY. And that's when we used the basis that was fixed to the ground. But when we use the basis that's fixed to the disk, we get R theta dot U theta. Now look at these two expressions. You can see that the first expression is more complicated than the second expression. In addition, the algebra that was required to get the first expression is more complicated because we had to actually take a derivative, we had to use the chain rule, we had to do all these things, and we had to work with sines and cosines. In the second expression, we didn't have to do any of that. So the second expression, the reason it comes out the way it does is because it conforms much better to the geometry of the problem. And here's what I mean when I say that it conforms to the geometry. So recall the diagram that we drew earlier. Here's that diagram. Now you'll notice that the direction of the velocity of point Q is in the same direction as U theta. If I draw this, that direction is along U theta. Now I'm going to try to get this as close to parallel as possible. But this is the velocity of point Q in G. And the velocity of point Q in G is in the direction U theta. And you'll notice that U theta is tangent to the circle. And that would make sense because this is circular motion. So as a result, you would expect that velocity to be tangent to the circle. So it's consistent with the geometry. It also winds up giving you a much simpler expression from what you would have gotten had you done this using the basis that was fixed in the ground. So using coordinates that are fixed in the disk gives you the advantage of being able to take advantage of the geometry. So once again, I'm going to remind everyone that this basis is fixed in G and this basis is fixed in D. Now, I'm not going to go through getting the second derivative or the acceleration using these coordinates that are fixed in the ground because it's not a good way to do it. And you can see that when you have to take this derivative again, if you use coordinates that are fixed in the ground, this is going to become an even more complicated expression because now you have a product that you have to deal with. It's theta dot sine theta, and you got another product, theta dot cosine theta, and you have to take the derivative of that with respect to time. That's going to be a very difficult and very mistake-prone process. But we are going to actually compute the second derivative, again, using the transport theorem, and we'll do that now. So suppose now that it is desired to obtain the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground. This quantity happens to equal the acceleration of point Q as viewed by an observer fixed to the ground. So that's the acceleration of Q as viewed by an observer fixed in G. But now let's start again with the velocity of point Q as viewed by an observer fixed to the ground. So recall the velocity of point Q in G is equal to r theta dot u theta. Now notice that this is expressed in coordinates fixed in D. But we want the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground. So because the original expression here, the derived expression, velocity of point Q as viewed by an observer fixed to the ground, is expressed in coordinates fixed in D, and we want the rate of change as viewed by an observer fixed to the ground of that velocity of point Q in G, we need to apply the transport theorem. So we need to apply the transport theorem. Now, how are we going to apply the transport theorem in this particular case? So let's see how this works. So we then have the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground has to equal the rate of change in the disk of the velocity of point Q as viewed by an observer fixed to the ground plus the angular velocity of the disk in the ground crossed with the velocity of point Q as viewed by an observer fixed to the ground. This time we're taking the rate of change of V, Q, and G. So as a result, in all three of these slots is the same vector, the velocity of point Q as viewed by an observer fixed to the ground. But in this case, it's a little more complicated because this first term in the transport theorem is not zero. So let's look at it. d dt in D of the velocity of point Q in G. Well, we recall that the velocity of point Q in G is equal to r theta dot u theta. But r we know is constant, and theta is changing with time, but u theta is fixed in D. So the only thing in this expression that changes when viewed from the perspective of the disk is that the angle theta is changing because r is fixed is a constant and u theta is fixed in D. So as a result, this rate of change becomes r theta double dot u theta because again, r is constant and u theta is fixed in D. So the only thing that's changing from the perspective of an observer fixed in the disk is the angle theta. Now the next term is a cross product, and that cross product is omega dg crossed with the velocity of point Q in G, which is equal to theta dot uz crossed with r theta dot u theta. So I just substituted in the expressions. That's all I did. Now, if you look, you'll see that the r theta dot can be moved out front, and so you just get uz crossed with u theta. Well, uz is the third basis vector, and u theta is the second basis vector. So the third basis vector crossed with the second basis vector is minus the first basis vector. So this is equal to minus r theta dot squared times ur. And now all we have to do is just add these terms together. So we get that d dt in g of the velocity of point q in g is equal to r theta double dot u theta minus r theta dot squared ur. But this is out of order because the basis order is ur u theta uz. So we put it back in the order of the basis, and we get minus r theta dot squared ur plus r theta double dot u theta. And as I said, this quantity is equal to the acceleration of point q as viewed by an observer fixed to the ground. So now we've applied the transport theorem twice. The first time we applied the transport theorem on the position of q relative to O, and we got the velocity of point q in g, and that was r theta dot u theta. We then took the rate of change of that as viewed by an observer fixed to the ground, and we got the acceleration of point q as viewed by an observer fixed to the ground. So this example provides quite a bit of structure with regard to how the transport theorem actually works, and it actually shows you that using an appropriate basis or observation, if you want to call it that. In this case, the observations that are the most useful are the ones from the perspective of the disk. And as a result, we can write these rates of change in a nice compact way that makes it possible to express things in a way that takes advantage of the geometry of the problem. That's the key thing, is that it takes advantage of the geometry. So that takes us to the end of this particular lecture. So in this lecture, to summarize, we first studied the transport theorem in more detail, and that allowed us to explain what each of the terms in the transport theorem meant. And then after studying the transport theorem in a little bit more detail, we provide an example to gain insight into the structure of the transport theorem. And that takes us to the end of this lecture. And this example hopefully will be something that can be revisited from time to time when perhaps it gets a little bit confusing to understand what's going on with the transport theorem. But in this particular case, we have a way of being able to bring it down to something as simple as possible in order to understand what all these different pieces in the transport theorem mean. And we'll end this lecture at this point. So this lecture can be summarized as follows. First, we provided the objectives of kinematics. And then we described reference frames and coordinate systems. And third, we defined rates of change of scalar and vector functions. And after that, we derived the rate of change of a vector in a rotating reference frame. And we called this result the transport theorem. And then we provided additional key properties of the transport theorem. And finally, we studied an example demonstrating the structure of the transport theorem. Now, the material studied in this lecture will form the basis of all kinematics that will be performed moving forward. But at this point, given the amount of material that's been studied in this lecture, we will end this lecture and we will continue the discussion in the next lecture.